Con agua nomás.
¿Su vaso de jugar?
Ujú.
¿Por qué no le gustaría alargar el estómago?
Sí, no le gusta.
Él es de Estados Unidos.
Sí.
No funcionó.
Está transmitiendo, pero todavía no le llega.
Ah,
Como está con la delay, ese atraso. Así que está bien. Y ahí está.
¿ya almorzó usted?
No conviene empanada.
Ay. A las que venden abajo.
Sí, que arriba, aquí comí yo.
¿Dónde?
Aquí arriba.
Ah, tercero.
Sí.
Ah,
No, quería completo, no había.
y aquí no hay completos mejores que ahora. Igual que son como un plástico.
Sí.
No, la pasta. Como en sobre. No es un bolsito. No es muy bueno.
Me imagino. Estos tres que los saludé, cumpleaños está haciendo doble. Ahí está empezando. Lo que pasa es que como está una hora más grande, más pesada.
¿Sabes que pararlo justo cuando termine?
Sí, si no sigue, sigue y sigue.
A ver si se graba.
Vamos a ver cómo se escucha. Sí, por lo menos soy más decente. Entonces, lo puedo leer, sí, un poquito. Oh, pero el sonido está como la wea ahora.
¿Sí?
Run concurrently. How many of you have a 1,000 core machine? Yeah, nobody yet, right? So this is something you're going to want to consider. The degree of parallelism times your job queue processes will roughly control the amount of resources this concurrent gathering will have on your system. If you have a 16 core machine and you're using a degree of parallelism of, say, 16, you probably don't want to use this because we're going to be using all 16 cores simultaneously for those parallel queries. Or maybe if I use this, I would set the job queue processes parameter to 2 to make sure that no more than 2 of these were running parallel 16 at the same time. So think about the amount of resources this could potentially consume, your degree of parallelism times job queue processes. If you need to be doing other things on the machine when the stats are being gathered, you're going to want to knock these numbers back, or perhaps not use one or the other. Maybe you use concurrent stats gathering to parallel query, or vice versa. Depends on the size of your machine. And if I use both together, that does allow me to do that parallel query against each one of these segments in multiple jobs. And again, that's a good thing, and that's a dangerous thing as well. Right? If you totally overload the machine, make it so that you can't even type ls or cd or anything else like that, you're going to end up pulling the plug and having to explain to your manager and friends why you did such a silly thing. And then you're going to have to try and unconfigure this quickly enough so that it doesn't happen again. Incremental statistics. This was introduced in 11G as well. This goes explicitly towards partition tables. And it was primarily designed for partition tables where you add a new partition, you load it, index it, gather stats on it, and then you don't touch it again, typically. So a rolling window in a data warehouse, for example. Now, with these partition tables, there were two types of statistics associated with them. There were local partition statistics, statistics on an individual partition, and then there were global table stats associated with it. The local partition statistics would tell us there's 1 million rows in each of these 10 partitions. The global table stats would tell us there's 10 million rows in the table. Why do we have two different types of stats? Because we basically have two types of queries. We have queries we know go against a single partition. Those queries are optimized using the local partition stats. Then we have other queries that are known to hit 0, 1, or more partitions. And those queries use the global table stats to be optimized. So at one level, we need to know there's 1 million rows in a partition if we have a query that's going to hit just that partition. At another level, we need to know there's 10 million rows in the table if that query is going to hit multiple partitions and deal with the entire table, not just a single partition. Computing global table stats in Oracle 10G and before was done simply by adding things up. I take the number of rows in each partition, add them up, that's the number of rows in the table. That worked well. But it also added up the number of distinct values that it computed in the partitions. And so if there were 10 partitions, 50 distinct values for a column in each one of those partitions, the assumption would be that there's 500 unique values for that column at the table level. If that number was wrong, we would get bad query plans. You rely on those estimated cardinalities to drive the cost of the query to come up with the right plan. And if instead of 500 unique values, there were only 50, that would be bad. And we were sort of forced in the past to generate not only local partition stats, but also global table stats. That added a lot of time to the stats gathering, and it wasn't very scalable over time. I mean, I have 10 partitions today. 10 months from now, I'll have 20 partitions. 10 more months from then, I'll have 30 partitions. Every time I go to gather global table stats, I have to read every single partition. So the time to gather stats would take longer and longer over time. So in 11, we introduced the concept of incremental stats. They allow us to effectively compute global table stats exclusively from the local partition statistics, meaning you do not need to gather global table stats reading every single partition ever again in this environment. The way it works is, as we gather local partition stats, we also generate what we call a synopses. This is that bitmap hashed representation of the unique values in a column I was talking about this morning. DBMS stats, when it goes to compute the number of distinct values, can do that computation for 1 billion unique values in about the same amount of memory space as it takes for 50 unique values. So using a very small memory structure, we can accurately compute the number of distinct values for a potentially infinite set of values without having to spill the disk, without having to write the temp. That's what made debian of stats faster. But when we take that synopsis and we store it to disk, so each partition has that little bitmap hash representation of its unique values for those columns, we can, after all these local partition statistics are gathered up, take these, merge them together, and get an accurate number of distinct values across all of these partitions. So now when we gather incremental stats, we not only gather the normal stuff we did in the past, but we save this synopses off to the side. As a new partition comes in, so that partition comes in new, we create the synopses for that, and then we can take all of the pre-existing synopses and sort of merge them all together to get the now correct number of distinct values. If you were to age an old partition off, the same thing happens. We would just drop that synopses and recompute the NBV based on the existing ones. What this means is, for those large partition tables, you never have to gather global table stats again if you're using incremental stats. What you would have to do to switch over to this is take your existing partition table, delete the statistics that are on it, enable incremental gathering on that partition table, and then go and compute the local partition statistics for each existing partition. You have to do that once to get into the new statistics format, if you will. But from then on in, you will only be gathering statistics against newly added partitions. If you're in an OLTP system, however, and you do most of your inserts, updates, and deletes against this current partition, but you still modify some of these old partitions in version 11G, you will find when we go to gather stats, we will gather stats against any local partition that's had at least one insert, update, or delete against it. So in the OLTP environment in 11G, this is not as useful. It was initially designed for data warehousing, whereby you're adding a new partition, loading it, indexing it, and then gathering stats against it, and it remains static. In version 12, they've changed this so that the simple act of modifying one record in this partition will not cause that partition to be reanalyzed. You can set up the staleness level on these partitions. So by default, you could say that until 10% of the data in these partitions has changed, do not gather stats against them. Okay, so in version 12, this will work very well for an OLTP system where you're modifying all of these partitions. In version 11, it's mostly geared towards a system where you add a new partition, load it, index it, and then don't modify it again. Okay. When not to gather statistics, this seems like a strange one. Of course, you always want good current statistics, but there's some situations when there's a bad time to think about gathering these stats. Volatile tables, temporary tables, intermediate work tables. These are all things that have issues with when statistics are gathered. If you're using the automated job to gather stats, when would it tend to gather statistics on all of your tables? Like in the middle of the night. When might a temporary table be completely empty in the middle of the night? When might a volatile table, a table that you use as a transaction table or a queue table during the day, it's empty in the morning, it's full in the afternoon, and then it's empty again at night, right? So it would be a bad idea for these tables to have statistics to be gathered during times of low activity in the database. You actually want to gather stats against these tables when they're at their largest. So for those Q tables, the data volume changes dramatically over time. Starts empty in the morning. It's got millions of records in the afternoon. By the end of the day, it's empty again. A good time to gather stats on that table would be maybe not even on the production system. We get into an environment where I can fill this table up with a ton of representative information, data that looks like what will be in there in general, gather stats on that table, export, import those statistics, set them against this volatile table, and then lock them. Don't let anybody gather stats against that table again. Or if this table has one of those columns that are populated by sysdate or a sequence, and you use that in where clause, follow this process, put the representative statistics in place, but then periodically come back with dbmstats.set column stats to increment those high values so that we get the right estimated cardinality. Your goal is not to have fresh statistics. Like, we use the word stale a lot in regards to statistics, but statistics aren't like bread. They don't go stale, they don't go bad, they don't get moldy. But rather, stats should be thought of as either being representative of the data that's in the database, they accurately describe what's in the tables, or the statistics do not accurately describe what is in the tables. Our goal with these sorts of tables that grow and shrink all over the time is to have statistics in there that represent what the table looks like at its largest size. We typically get that by preloading the table, gathering stats, locking those statistics in place, and then using some dbmstats.set, say set column stats, to adjust high values if we have sysdates and sequences and things like that going into it. Intermediate work tables. Use these in your reporting warehouse. Let's SQL load into a table, then we massage, reformat the data, we put it into another table, and then we do some work against it, and then we finally put it into the real table. What sort of statistics should we have on those two tables that we just loaded into, and then we took the data and worked it into the other table, and then we took it from that table and loaded it into the real production one? In that case, for those two tables, those two scratch tables, those two work tables, we might not want any statistics in place on them at all. One approach we could take is to use a thing called dynamic sampling. If you query a table that has no statistics, we will, by default, use dynamic sampling to figure out how big the table is, some of the column values, high and low values, things like that. So at hard parse time, we will do a mini statistics gather for that query in order to optimize that query. In an environment like this, as part of an ETL process, I'm not doing hundreds of thousands of queries against these work tables. I'm doing a couple. The dynamic sampling overhead is fine in this situation. We'll spend more time parsing, hopefully to get a better query plan. But we're not running hundreds of thousands of queries against this. We're running 10, 20, 30 queries against this, each of which will spend a little bit of time sampling. So dynamic sampling would be appropriate. And I'd suggest a dynamic sampling level of, say, 5 or above if you're using it in this circumstance. Level 2 gets very basic statistics. Level 3 gets everything level 2 does, but it also looks at some single table guesses that it had to make. Level 4 does everything level 3 does, but it also looks cross table when looking at cases where the optimizer had to guess. And level 5 is simply everything level 4 does, but a little bit larger of a sample. And 6 is everything 5 is, just a larger sample. So everything from 5 on up is just a bigger sample size. So level 5 for a job like this would probably be appropriate. And you can just put that into the query itself as a hint. That's one approach. Or in this ETL process, you could use an alter session to set the dynamic sampling level in that session to be level 5. so that all of the queries that it's running would go through this dynamic sampling process. And then some other types of statistics. Dictionary statistics, fixed objects, the X dollar table, system statistics, and automatic dynamic sampling. Dictionary statistics, these are stats on the Oracle dictionary itself. These tables and their statistics are most relevant to the people in this room, actually. You guys run queries against the data dictionary all the time. Your performance tuning tools, the scripts that you run, everything else. The SQL we run, Oracle runs against the data dictionary, is in general all index access. When we go to parse a query, it's all index reads. Statistics for those sorts of queries doesn't really count. We know that we want to use the index to get a single record. But when you start running queries like how much free space is in the database, how many objects are there, what do the statistics look like for these 1,000 objects sitting there, those are the sorts of queries that are going to need relevant representative statistics against the dictionary. This is up to you guys to make sure it gets captured. If you're running the auto job with all of the defaults for gathering stats, this is happening. If, on the other hand, you have disabled that auto gather job, this is no longer happening. Instead of disabling that job, earlier this morning I suggested you might just want to change the input to it to set the auto stats level to Oracle. That will cause the job to not touch your tables, but it will still touch our tables. And that will cause the Oracle Data Dictionary tables to have statistics gathered during your maintenance window. If you don't do that, make sure that you do incorporate the Oracle Data Dictionary tables into your statistics gathering routine so that we have representative stats on that. Then there's the fixed object stats. These are stats on tables that start with X dollar. They're in-memory data structures. They're really not database tables. On top of these X dollar tables, we build the V dollar views. And you guys query the V dollar views all the time. Now, when should you gather stats on these guys? Well, you can't do it when the database is idle. Because when the database is idle, how many rows are there in V dollar transaction? There's none, right? Because you're not actually doing any work in the database. V dollar session is going to have very few rows. Many of the tables will appear to be empty. So we want to gather these stats when the database has a significant amount of work, but there's a danger to that because these X dollar tables, sometimes we use latches to access them. So if you have a very busy system and you gather the fixed object stats at peak utilization, you're actually going to be adding some concurrency issues into your own database. As you're querying an X dollar object, somebody else might not be able to query or modify that object at the exact same time. So this is something we have to do a little bit carefully. We'd like the system to be loaded. We'd like a little bit of extra capacity to be available. And we don't have to do it that often. That's the good part. It's not something you should do every day or every week or even every month. You might want to do it after a major parameter change. If you change processes, that's going to change the size and shape of the SGA, the data structures in the SGA, change the size and shape of these X dollar structures. So after a major version upgrade or after changing an init.org parameter that really changes these data structures like processes, sessions, transactions, things like that, you would need to consider gathering these statistics again. And again, this is going to mostly affect the DBAs and such, because it's going to affect the performance of queries that go against the V dollar structures, which are simply built on top of these X dollar structures. Again, if you're fully loaded, running at hundreds of thousands of transactions per second, and if you breathed on the computer wrong and caused something to crash, that would be a wrong time to gather these. Right? You want a little bit of excess capacity because you're going to be introducing some additional work, and a little bit of extra latching. Then system statistics. These are the statistics that measure our single block I/O speed, multi-block I/O speed, and our relative CPU speed. And they're used to cost out how much a single block I/O or multi-block I/O or a specific CPU operation would cost. These numbers come into our CPU and I/O costing inside the query plans. That number you see as the cost of the query are directly affected by these three numbers. Our suggestion would be, let us work with the default workload stats. The stuff you have in there by default is what you should have. There's some extreme cases, say on an Exadata, an engineered system platform, that we want to play around with these numbers. But for the most part, don't pay too much attention to these. The defaults that are in place are correct for almost everybody. Run with those. If you decide to gather your own, you're going to affect every single query plan in your system. And that could be a good thing, that could be a bad thing. It might mean nothing at all, but it will mean that you're entirely different from everybody else in the world. And so in general, we would recommend just going with the defaults. And this is, you'll have access to all of these slides, by the way. They're actually already up on asktom.oracle.com. I've uploaded them a couple of times. But these would be some white papers and links that are useful for going over the stuff I talked about here. Before I continue on, any questions on gathering statistics? So now we'll start to take a look at interpreting the explain plan. We've already seen this slide this morning. This is what every single statement goes through as part of being processed. You know, we've got the soft parse that takes place here. If we can't find anything in the shared pool, we go to the query transformation and we generate this plan. And this is what we're going to be looking at now. Is these plans, what they look like, how to interpret them, what you're looking for when you're trying to tune a query. So first, what is an execution plan? In its simplest form, an execution plan is a human-readable bit of pseudocode that tells you what we're going to be doing. It is not a compiled plan. It's a report. It's like an outline. It's just a textual report of what we're going to do. It doesn't contain all the information. That happens down here in the code generator. It's just enough information for you to get an idea of how that query is being processed, how it's being approached. There's a couple of ways to get these explain plans and look at them. And this is probably the most familiar with most people. This is the one I use all the time. It's tabbing. It works on a VT100. It works on the terminal. It works on a GUI bitmap display. It's just a linear sort of report format. You look for the furthest indented part of the report. That's where everything starts, and you read it from the bottom up from there, and that's how it all comes together. If you're using, say, SQL Developer or Enterprise Manager, there's also a tree representation. And this has some advantages as far as the display format goes, because you can click on the nodes and they collapse and they roll up and they roll down and everything else like that. And it makes it sometimes easier to visually, review the information. I'm going to be concentrating on this one because it works in all environments. So how to generate a plan? There's two ways to do it. There's an explain plan command. I will call that the wrong way, the bad way, the way we did it last century, the way we shouldn't use ever. And we also have $SQL plan, which is the way we should be getting all of our plans now. The difference between these two, explain plan takes a SQL statement and right there, right then, in isolation, develops a plan for it. It has access to very little information. I'll show you some of the bits and pieces that it's missing. And the explain plan you see is the plan that would be used if all of the missing bits of information it doesn't have access to weren't available to the optimizer. Another way of saying that is what an explain plan shows to you is today almost never what the optimizer would actually be showing to you. So an explain plan is in many cases, you might even say in most cases, an inaccurate representation of what happened. When all we had was a rule-based optimizer, explain plan was perfect. The plan explain plan came up with was exactly the plan run by the optimizer. Once we introduced the cost-based optimizer back in version 7, what explain plan shows to you is what might happen. What actually happens can be different from the explain plan. So at one point in time, prior to 1992, that's going back 22 years, explain plan was perfect. Ever since then, explain plan's been getting less and less and less useful. So let's take a look at the explain plan. This is the way you use the explain plan for select blah, 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 from wherever. That populates a table called a plan underscore table. It's typically installed by default these days into the database. And then the way to format it nicely is to use this package, dbmsx plan. This was introduced in OracleMania, .display. And to the .display, you send it the name of the table. And optionally, when I do the explain plan, I can name this. So I can pass in the name for this, or if I leave it to be null, it finds the last explain plan in there and dumps that information out. Explain plan should hardly ever be used. You have to be careful when using auto trace and related tools. If you're in SQL Plus and you set auto trace, trace only explain, the plan you see is an explain plan. If you're a SQL developer and you ask it to explain it, it's going to be an explain plan. If you're in Toad, it's going to be an explain plan. Never use explain equals username password with tkproc, because if you do that, you'll be using an explain plan. The explain plan may be radically different from what actually happens at runtime. I would avoid using dbmsxplan.display. We used it right here. That reads that plan table. We want to use display cursor, which will use $SQL plan. $SQL plan looks just like a plan table. The $SQL plan is full of plans that were actually generated and used, whereas explain plan is a fantasy. This might happen, probably won't, but it could. Right? We want to look at what plan was really used. And here's an example of explain plan line. I'm going to create a table. I'm going to have a column I call ID, start with number 99 and all of it. I'm also going to take object ID, which is a number, and store it as a string for whatever reason. And I'm going to do this for 20,000 records. I'm going to take that ID column and for one row, set it to the number 1. So this is very skewed information now, right? Create an index on that ID column. Some people might say that's a stupid index, right? Because there's only 2 values in that column. Nobody indexes something for 2 values. This index is awesome for finding that row, right? And if you frequently want to find that row, you better have this index. You don't want to be full scanning every time. And then we'll create an index on that string column. Now remember, that string column is really a number hiding in a string, something a lot of developers do. We'll gather stats on this table. I'm violating every rule I told you this morning, right? I told you I just want these 2 things. This is a demo. I want this to do the same exact thing every time anybody runs it anywhere. So I'm telling it estimate percent of 100. I want you to look at every 20,000 records. You will get the same statistics in your database that I have in my database. And I also want to go out of my way and say, take every index column and generate a histogram on it. Remember, Oracle will automatically generate histograms on skewed columns, but only after I've queried the data to tell it I use it in a where clause. So if I didn't tell Oracle right here To do this, it would not generate a histogram on this column for me. And for this demo, I want to make sure I have a histogram. So in real life, you won't do this. I need a volunteer. This is going to be tough, I know. Anybody? Okay, I'll be the volunteer. I volunteer. I have select count star from T, where ID equals :n. Now, let me give you some information about table T. Table T has 1,000,000 rows in it. ID equals :n. This ID column has 10 distinct values in it. What cardinality should I estimate? How many rows will come out of this query? 1,000,000 rows, 10 distinct values, 1,000,000 divided by 10. On average, that should return 100,000, right? In this case, my 20,000 row table, I'll go back and think about the 20,000 row table. I totally messed up my example. This is a 20,000 row table. ID has 2 values. 2 in the 20,000, 10,000. And that's exactly what AutoTrace is thinking, right? But remember, we have a histogram on the ID column, right? So the optimizer knows when ID equals 99, it's going to get 19,999 rows. And furthermore, the optimizer knows if that was ID equals 1, it's going to get 1 row. So where's this 10,000 coming from? I mean, because we did the auto trace after defining a bind variable and setting it to a value. Why isn't this 19,999? Answer: explain plan does not bind P. Explain plan optimized where ID equals $. Explain plan didn't have any of the bind inputs. So explain plan had no value for ID to compare to. It optimized literally ID equals I don't know. And if it's ID equals I don't know, it can't use the histogram, so it simply used NDV, number of distinct values, and num rows. And that's where the 10,000 came from. If I actually run the query with ID equals 1, it knows 1 row, right? Because it actually has that value. If I run it with 99, it knows 19,999. At no point in time, would the optimizer ever use 10,000. Because the real optimizer waits until the bind variables are supplied, right? And then does the parse right before it does the optimization right before it executes the query. Explain plan is showing us a query plan that the optimizer would never, ever develop. You'll never see the optimizer come up with 10,000. Because the optimizer would always have access to the bind variable. Explain plan doesn't. Here's another thing down here. It says ID equals to number of :n. N is already a number. Why is it doing that? Explain plan doesn't only not have the ability to bind P, explain plan knows nothing about any of the data types of the bind variables. Explain plan assumes that every bind input is a character string. So if this was where date equals :x, it would assume that you're comparing a date to a string. If this is where number equals :n, it would assume you're comparing a number to a string. And that's exactly what it did down here. It converted what it thought was a string into a number. This entire plan, nothing that the optimizer would ever come up with, period. So the optimizer comes up with this correctly as part of an auto trace, as part of an explain plan, but only because there are no bind variables in this. Add a bind variable and all bets are off. But it knows if the initial input was 1 or 99, what the estimated cardinality should be. So here, I'll do an auto trace only explain, select object ID from T where I'm using string ID now. That's string column, and I'm comparing it to :n. Now, :n is defined as a number, right? Now it's going against the string ID column, and there's an index on that. And this all looks correct. This looks like a good thing right now, right? The programmer ran this. They'd be pretty happy with this. They'd say, this is good. Did any of this happen? Could any of this happen? Think about it. This is string equals number. When we compare a string to a number, one of the two values has to be converted into the other type, right? But when we compare a string to a number, we convert the string into a number to do the comparison. This is saying we're comparing a string to the number. This is explain plan again. Explain plan doesn't know the bind types. It thinks this is a string. It thinks it's comparing a string to a string. Now, when it compares a string to a string, it can use the index range scan, table accessed by index row ID. It got the estimated cardinality right because it knows that there's 20,000 rows in the table. And it knows there's 20,000 distinct values, NDV for this. It did the division and said one row. Let's use the index and do that. But that's not the plan that was actually used. If I select object ID from T where string ID equals :n, we get the one row we're expecting. And then I use DBMSXPlan.display cursor. By calling it this way, without giving it any inputs, it retrieves the plan of the last query executed in my session from $SQL Planner. So that's pretty nice. So it gets the plan for the last query executed, and it turns out it was really a full scan. Notice it's getting one row, but it full scanned all 20,000 rows. Why? Because there was a to number wrapped around string ID. I have an index on string ID. I don't have an index on to number string ID. Okay? So the explain plan in this case, the developer looking at this would be totally misled by what will actually happen at runtime. If you want to see what the plan for a query is, you're going to have to run the query. You're going to have to run the query and fetch at least one row from it, and then we can see the actual plan that's generated for that query. And you do that by reading it out of the $SQL plan. And the easiest way to do that is just to run a select like this right after you run a query, and this will grab the plan of the last query executed in your session. Now, some of you might ask, and I've gotten this question a lot, why do we convert the string to a number? Why didn't we convert the number into a string? And the answer is sort of simple. In certain parts of the world, they use commas where you should use dots, and dots where you should use commas. And also, there's multiple ways to represent the same thing. These are all the number 0. But if we converted the number into a string, maybe none of those would be the number 0. Right? It would depend on our default NLS settings, our NLS numeric characters, or number formats. Right? So depending on how you have an environment variable set, all of a sudden that could affect your result set if we were to convert the number into a string. We always take the less specific type. String is less specific than number, and promote the less specific to the more specific. So if I'm comparing a date to a timestamp, the date will be converted to a timestamp. I compare a string to a number, the string is converted into the number. Okay? And these implicit conversions do a lot of making indexes not usable, and we won't necessarily see them in a straight explain plan. So hopefully I've convinced you to not use explain plan going forward. Be suspicious of auto trace. The only time you can really use auto trace with the explain plan is if you are not using bind variables. If you have a single bind variable in there, the explain plan is probably wrong. So that display cursor is the way to get it. I can run a query, use xplan display cursor, send in nulls for the first two, and it gets the last query executed in my session. I can also send in a specific SQL ID and that will give me all the plans for that SQL ID, or I can send in a SQL ID and a child number, and it will give me the plan for a specific cursor number. The DBMS X-Plan display cursor takes 3 parameters, by default the SQL ID and child number. If you let those default to null, again, you get the most current query in your session, and then the format for the report, which defaults to typical. The format is highly customizable. We'll be taking a look at quite a few of them as we go through some more of the examples here. Yes?
So I don't understand. If we want to make the UX campaign, it was just to last one, we have to run the query, or we can have going to say, hey, this is the query where I want to execute my statement. Do I need to bring all the rows? Or
Okay, so the question is, I want this. I want the actual answer, right? I want the plan that will be used for my query. I don't want this explain plan because I now understand how wrong it can be. I want this. Do I have to run the query in order to get this? And the answer to that is, you have to start the query, but you don't have to complete it. Because the steps we go through, when you call prepare statement, you send the query over to us. We don't have the bind variables yet. If we don't find the query in the shared pool, we don't optimize yet, because we don't have those binds. Right? We wait for you to call bind, bind, bind. When you call execute, when you actually open the cursor, that's when we optimize the query. That's when we populate the $SQL plan. So you have to fetch at least the first row from the query, and then you can see this information. Because until we go to get the first row, we haven't developed the optimized query plan yet. Now, if it takes you 5 hours to get to the first row, you don't actually have to wait for the first row. You have to wait long enough for us to get to the point where we're trying to get the first row. Right? So if you have a really long running query, it takes an hour to get the first record, and you want to see what the plan was, there's 2 things you can do. One, start the query running, wait an appropriate amount of time, hit Control-C, and then use this select, and you'll be able to read the plan out. Because we've gone through the entire optimized phase. A better, more 21st century way, start the long-running query, hop over in Enterprise Manager, get into the real-time SQL monitor. That allows you to attach to a running query. And you get a graphical representation of the query plan. And you also see in real time how many rows are flowing through each step in the plan. Right? But to get the real, honest plan, that query has had to have gone through the optimization phase, and that's just the last thing we do before fetching the first record. So typically you have to fetch at least the first record, or wait long enough to know that we've gotten through optimization and we've started to go after the first record. Right? That's when you see it in $SQL. So, what is a good plan? I mean, if you're looking at a query plan, you want to decide, this is good or not. Well, the way the optimizer is looking at it is there's 2 different ways to approach a plan. One is for serial execution. There, it's all about the cost. So normally, for most of us, in almost every situation, the lower the cost, the better the plan is. However, take a step back. What generates the cost of a plan? It's all based on those estimated cardinalities. If we think we're going to get 2 rows out of 1,000,000, and we cost getting 2 rows out of 1,000,000 using an index, that's probably going to be the cheapest way to go. But if we actually end up getting 250,000 rows out of 1,000,000 through the index, we obviously made the wrong choice. But when we start going parallel query, It's not about lowest cost. With serial query, it is 100% all about the cost. The less resources we use, the faster the query goes in serial execution. So serial execution is all about minimizing the amount of resources we use. However, when we get into parallel execution, it's totally opposite. In parallel execution, if you were all my parallel execution servers, the fastest way to get something done would be make all of you do a whole bunch of stuff for 3 minutes continuously. It's about abusing your resources. It's about using every possible resource available to you. There might be lower cost plans that use less resources, but because I have parallel execution, I'm not worried about that. I want to exploit resources. And that's why when you alter a table parallel and you run a query against it, you might say, hey, there was a serial plan that was like a lot cheaper, but you went parallel. That's because you asked us to go parallel. You ask us to go parallel, we're almost always going to go for the query plan that uses the most resources possible on that machine. It's all about maximizing that resources. Now, in version 11, there is some control that the DBA has over this. In version 11, when parallel queries enable, we're always going to generate a serial plan. And if that serial plan is thought to run faster than fast enough, we'll use that serial plan. There's a time threshold that the DBA can set. The DBA can say, if your serial plan is going to take 15 seconds or less, go ahead and run that, even if you have parallel plans that you're considering. If you have 15 seconds or less, use that serial plan. So in 11G, it's a little bit of a mixture of this. There's a threshold set by the DBA that says, use serial plans as long as they run faster than this. But if they start to take longer than that, and we're allowed to use parallel, we're going to throw out the serial plan regardless of the cost, and we're going to go ahead and do it in parallel. Because most of the time, the cost of the serial plan would be less than the cost of the parallel plan, because the parallel plan is looking at doing full scans and this and that, and it's throwing every resource possible at the problem. The more resources we throw at it, the higher the cost. So it gets a little bit confusing when looking at the cost in a warehouse system versus in OLTP. What is that cost? Is it just a magic number the optimizer makes up? Resources required to execute a SQL statement, an estimate of how long it will take to execute the SQL statement? It's actually the resources. It's taking a look at the resources required, both I/O and CPU, in order to execute a SQL statement. If you get a query like select star from table where index column equals 5, and you see a plan that says index range scan, table access by index row ID, it's got a cost associated with it. That cost is going to be a direct function of the number of rows assumed to be returned by that query. Let's say that query, the index column goes through the index to get to the row ID, one more I/O against the table. Another query, select star from the table where index column equals 100. Maybe that index column is not unique, and it's assumed that that is going to return 1,000 rows. The cost for that query might be, I think I have to do 5 I/Os through the, but that cost is a function of the number of resources. How many I/Os do I think I'm going to perform? And how much CPU do I think I'm going to use performing those I/Os and any expressions in the where clause. In a perfect world, this would tell us that. If we know the number of resources you're using, and we have your I/O speeds and CPU speeds and everything else, we'd be able to turn cost into time. And in fact, we do. You'd probably see a time estimate in some of your query plans. That's us attempting to turn the cost into time. In a perfect world, it would work really well. Since we're dealing with estimates, that time is just a guess. It's not perfect. So don't look at that time and say, oh, my query will come back in 3 seconds. It'll come back in about 3 seconds if all of those numbers that made up the cost were accurately generated. What is performance? Yes?
The traffic network is part of the internal Oracle function, the traffic network.
The actual network back and forth to the client.
Yeah.
The network back and forth to the client is not costed into the cost of the query at all. So we look at nothing outside the database. So SQLnet round trips, your SVU size, whether you're on optic or tin cans and strings, we don't take any of that into consideration when costing a plan. What about performance? Is performance getting as many queries completed as fast as possible, or getting as fast as possible elapsed time using the fewest resources, getting the best concurrency rate? It really depends. Your performance has many different aspects. In an OLTP system, performance means one thing. In a reporting system, it means something completely different. In general, for an OLTP system, performance is the fastest possible response time for a given query. The same in a warehouse. I'd like the fastest possible response time for a query. But many times in a warehouse, the fastest possible response time for a given query is going to give us really horrible concurrency. Why? In order to make this query run in 30 seconds, I need to use all 128 cores all by myself, and the 5 terabytes of memory you have, that's all about me. Every IO channel, that's all mine. You give me all that, I can run in 30 seconds. So when the database is optimizing a query, it's in general going for performance. We're trying to finish the query as fast as possible. We do have these two competing goals of serial execution versus parallel execution. We may be able to get a query done quicker using parallel, but that's definitely going to affect your degree of concurrency, for example. If we go parallel 32, you're not going to be able to have 1,000 people running concurrently, right? So it's really a trade-off. When we're looking at performance, we want the fastest possible response time, but we also do have to look at resources as well. Something that gives us the fastest possible response time on a query might make it so that our machine can only run one query at a time. How many of you would allow your machine to only run one query at a time? Anybody? What if I told you you could get 1,000 times more queries run through your system in a day if you ran them one at a time? How many people would do it then? How many people are never ever going to put up their hand no matter what I ask? Actually, that's in a parallel environment, resource management is critical. Right? If you have a 32-core machine and you decide to let people do parallel 32, which is I've already described, might actually be parallel 64. Right? You might fire off 32 producers to 32 consumers to a query coordinator. So you have a 32-core machine. How many parallel 32 queries can you run simultaneously? Maybe 2, maybe 3, maybe 4 if you have really slow I/O, right? But definitely not 10, absolutely not 100, and nowhere near 1,000. Right? But on a 32-core machine, what if I decide to let people do parallel 128? I can get my queries done instantaneously at 128, but only if I'm the only one running. Because if 2 people try to do it, that's like parallel 256, and that's way more than my 32-core machine can do. So resource management, limiting how many people are running parallel queries simultaneously is really important. When parallel query was invented in version 7.16, way back in 1994, it was invented to allow one user to use the entire machine. Was anybody, how many people were using servers in 1994? First of all. According to this poll, nobody, but there was probably at least one person. Do you remember what a big server in 1994 looked like? Memory was measured in megabytes. Right? Disks, if you had a 9 gigabyte platter, that was real big. And so to have lots of storage, you had hundreds of disks. You had maybe 512 megabytes of memory, and if you were lucky, you had 4 or 8 486 chips inside the machine, meaning you had significantly less power than I have on my cell phone right now today. I have more memory, more CPUs, faster CPUs, better I/O bandwidth than a server from 21 years ago. Serial queries were all we had, and they ran really slow when they were going against large sets of data. So we made it so that one user could use all 4 cores, all 512 meg of RAM, all the I/O channels. But you could literally run one query at a time. And the only reason you can run more than one query in the data warehouse today is because we have machines that are much larger. And we only allow individual users to use a small slice of that machine. This is just a word from the wise. If you have a warehouse and you're not controlling the number of active sessions using the resource manager, how many sessions can actually be active running parallel queries, you're just asking for trouble. Because it might work with 5 users running parallel, it starts to fall apart at 6, and if you ever got to 10, you're pulling the plug on the machine. Right? So this resource management is really important. But let's take a look at execution plans and start to understand the bits and pieces inside of it. Cardinality, the most important word that we're going to say today. We gather statistics so that the optimizer can estimate cardinalities. Cardinality estimates are what drive the cost for the various steps in the plan. If we get that cardinality estimate wrong, we probably have the wrong query plan. If anybody ever gives you a query plan and asks you if you think that's a good query plan, you can actually give a definitive yes or no answer. It's pretty easy. All you need to do is look at that cardinality column, and if you know the data, and you can say that those cardinality estimates look accurate, they look correct. This where clause will get this many rows. When I join this table, I'll have this many rows, and so on. If you look at that column and it's correct, you have a good plan, short of a bug in the optimizer. But if somebody gives you a query plan and you look at that column and you say, this where clause is going to return 10,000 rows, it thinks it's getting 10 rows, I would look at that and say, that's probably a bad plan. This is the most important number of them all. We're looking at a query plan, this cardinality. We want to make sure that it's close to reality. And we estimate this, right? We've been through a couple of estimates. The most simplest one is a single column equality predicate is the number of rows of the number of distinct values. You have 100 rows, 10 distinct values, cardinality is going to be 10. Right? If we have histograms, we might be able to get a more accurate number. But more complicated predicates, and by more complicated, I mean it has more than just x equals something. It has x equals something and y equals something. That's complicated already, because all we're going to do is take the probability of x, multiply it by the probability of y. What if there's a relationship between those two columns? What if they're correlated? You know, I said x equals 5 and y equals 10. It could be that when x equals 5, y is always 20. Right? And so our cardinality estimates would be off because there's some relationship. Why should you care? Wrong cardinality, wrong plan. Or more specifically, if you have a bad query plan, it is caused because we have to look at ways we can fix that. So, for example, taking a look at this plan, we have the estimated number of rows here. I'm looking at this to see if this is a good plan. I might start with step 6, filter, department name equals sales. Let's see, I know the department table a little bit. And tuning the query, if you don't know the data that the query is going against, you don't stand a chance of being able to tune it. But I can look at this, department name equals sales. Department name might not be unique, but department name is pretty close to unique, right? So I already know that if I'm going against the department table, department name with an equality, that had better show up with an estimated cardinality of pretty close to 1. So I can go up to step 6 here, table access full, departments 1. That was pretty good. That means that that was correct. Then I have to go through these other steps in the plans, like a table access full of employees. It's assuming that's going to return 107 rows. You know, does that number look accurate? Are these numbers correct? If these numbers are correct, I'm looking at a good plan. If one of these numbers is off by orders of magnitude, I'm probably not looking at the best plan. Sometimes we get the right plan by accident. So having an estimated cardinality that's way off doesn't mean that you have a bad plan. But if you have a bad plan, it definitely means one of these numbers is way off. Here's another great tool we use. This hint is not an optimizer hint, but rather it causes the compiled plan to remember more information. It gathers statistics about the runtime execution of the SQL statement. So you have to actually run the SQL statement for this to work all the way to completion, not just the first row. But we would say gather plan statistics. And I've got my query here. And then afterwards, I would use dbmsx plan display cursor. And I'm going to use a format called all stats last. All stats says, hey, if you have statistics from gather plan statistics, show them. Last says, just show them for the last execution of that query. I don't want to see them over every execution of that query. I just ran this in a session. I want to see my stats. So that's what the last one is. And this is the plan we give. And notice these two columns here, B rows and A rows. This is the estimated number of rows given to us by the cost-based optimizer. This was the actual number of rows observed at runtime. Notice that in this case, these two columns are identical. This will almost never happen to you in real life. In real life, this was 72 and this was, I don't know, 100. That's closer than close enough. But if this was 72 and this was 6, that's off by more than an order of magnitude. Right? If I can multiply or divide one of the numbers by 10 and get it close to the other, then it's off by that order of magnitude. So 100 would be okay, but 6 would start to be too far away, and I'd be suspicious of that. And I'd want to look at that step in the plan and see, how can I get the optimizer better information? Am I missing statistics? Does it have a complex predicate there that extended statistics could help fix? Would a SQL profile help fix this? SQL profile just takes a SQL statement and it executes pieces of it and figures out how many rows actually flow through it and feeds that information to the optimizer. Dynamic sampling might be able to fix it. You know, removing a function from the database column and putting it onto the bind variable could fix it. Instead of having function on database column equals constant, I have database column equals function of constant. That helps me get better estimated cardinalities. And in this case, this looks perfect. And this is for free. Everybody has access to this from 10G and above. Another approach would be to use the real-time SQL monitor that I mentioned. The real-time SQL monitor allows you to, from Enterprise Manager, to attach to an already running query that's taken an hour to run and you want to see where it is. The real-time SQL monitor will allow you to do that. It will also show you these numbers in real time. That can also give you a hint as to whether you should let a query finish or kill it. Right? Because if you're in the real-time SQL monitor and you say, this was supposed to return 72 records, but it's returned 7.2 billion records so far, and it's still increasing, I would be very tempted to kill that query right then and there, because it might never finish. Right? Because the actual and estimated are so far apart. I'm going to look at why we got so far apart and try to fix that first. Checking the cardinality estimates for parallel execution. So I tried to do the same thing. I took that query and I ran it in parallel. I noticed that the estimated rows, you know, those numbers look pretty familiar, but the actual number of rows are all 0 until the very end. How did that happen? Well, it's how parallel query works. There's parallel query coordinator, and then there's a series of parallel execution servers. Parallel query coordinator is a lot like a manager. Manages lots of people. Managers, in general, don't do the heavy lifting. They don't do the work. The parallel execution servers did all the work. But if we say all stats last, this is only getting the stats. In order to accurately see that, you're going to want to use the real-time SQL monitor, or we could do all stats all. If I did all stats all, it would take every execution of this query and aggregate it up. This can be very misleading as well. Because if this query was run 2 or 3 or halfway through in Control-C and things like that, all of those numbers would be jumbled in. This is the right way to approach it. In real-time SQL monitor, it will give you that graphical plan, it will give you the estimated rows, it will give you the actual rows and fill them in real time. But you see all these little groups of people over here? It allows you to drill down and see the individual parallel execution servers as well. And you can see if we've done something stupid, like really overwhelmed one of them. Our distribution method wasn't evenly distributing data across the parallel execution servers or something like that. But it gives you the ability to monitor and diagnose a parallel query for the first time. So incorrect cardinality estimates, some solutions to it. You have non-representative or missing stats. Go ahead and gather. Data skew, you might need to create a histogram. Multiple single column predicates on the table. You have this all over the place. And I bet if you start to go back and look at them, and now that you know that we just multiply the probability of X times the probability of Y times the probability of Z, you could look at many of your where clauses and say, yeah, it doesn't stand a chance of getting the right cardinality because these things are so interrelated that the cardinality estimates are going to be way low. We shouldn't be multiplying all those together. Well, go gather some extended stats on that. A function wrapped column, meaning a database column that has a function against it, that's going to be that 1% guess. Where f of database column equals value, 1% of the rows come back. Well, you probably don't want extended stats on that, or see if you can move the function to the other side of the equation. Right? Don't apply the function to the database column, apply the function to the constant, the literal, the bind variable that you're sending into the query, if at all possible. Then we'll get the right cardinality estimate. Multiple columns used in a join. We might need, again, extended stats on that. If you have anything beyond a single column key, when we do those join estimates, we have the same problems estimating the cardinalities as we do with single column predicates on a table, multiple single column predicates. We have a hard time estimating cardinality. So if you are using 3 columns to join table T1 to T2, you may want to consider creating extended statistics on those 3 columns you use in the join. Complicated expression containing columns from multiple tables. Here's where dynamic sampling can come into play. Let me take a column from table 1 and a column from table 2 and add them together and divide by 2. So I'm taking the average of these 2 columns and I'm looking for everything that's greater than 500. That's impossible for the optimizer to estimate cardinality. Dynamic sampling at level 4 or higher can take these cross-table sort of expressions and start to dynamically sample it to come up with a better cardinality estimate. So in a reporting system, for example, consider using dynamic sampling level 4 or above. I recommend it 5. It does everything 4 does, but takes a slightly larger sample. Access paths. We've got many of them. Full table scans, table access by row ID, and its unique scans, and the trade scans, and so on. The access path, again, is dictated by the estimated cardinalities. Lots of rows, full scans. Few rows, index range scans. So they're very easy to pick out inside of the explain plan. You can see all of these access plans here. You should just become familiar with what they are, how they operate, And understand that there is no best access point. An index is not the best. A full scan is not the best. It depends on the circumstances. If the wrong access method is being used, check that cardinality. It's always going to come back to the cardinality again. Do a quick quiz and then we'll take a break. If I get some feedback. I hear words coming from that side. We have a country table containing 10,000 rows, has a primary key on country ID. What plan would you expect for this query? Select country ID name from countries. There's 10,000 rows for country ID that's unique, has an index in 1, 2, 3.
Access index row.
Index unique scan, table access by index row ID, and in this case, an in-list iterator, right? Why? Because of the cardinality estimates. We are estimating we're going to get 3 rows out of there, right? 10,000 rows, primary key and country ID. What would you expect for this? Country ID name from countries, or country ID between 1 and 7.
Index range scan.
Index range scan in that case, and table access by index row. Pretty straightforward. 10,000 rows, primary key on country ID. What plan would you expect for this query? Select star from countries where name equals USA. Full scan, yes, because we don't have an index on name. So common access path issues using a table scan instead of an index. A couple of them are estimated, right? If I think I'm going to get a lot of rows, I'm going to go for a full scan and not use the index. First step is to check that cardinality estimate and validate it. Or it picks the wrong index, same thing. Cardinality estimates, the stale or missing statistics on the indexes itself, and so on. So for that